Yeah. So what do we know about derivative? The derivative of a function is, we all know that the derivative of a function in the interpretation of it is the slope of the tangent line to that function. Okay, so let's remind you of the drawing. So let's say here I have a function. All right, and let's find the slope of the tangent line to 2 points. So let's pick this point. This point is the let's say the x coordinate. Sorry about that. Day 2. I lost my thing. Okay, there it is. All right, so let's look at this function, and let's take 2 points. I'm gonna take this point, whose x coordinate is just x, and the y coordinate is just f of x. And then take another point. Okay, so some later point, go h units away from x. Here is h units away from x. So then the point corresponding is going to be, the x coordinate will be x plus h. And of course, the y coordinate is f of x plus h. Okay, so you have 2 points right there. And we are interested in the slope of the line through these 2 points. Okay, does anybody know what this line is called? What is this line?
Tangent line?
No.
No?
No, not tangent. Yes, who said that?
Nicolette.
Thank you, Nicolette. Yeah, that is the secant line. Very good. Not tangent. Tangent line is also known as the kissing line. It's the line where the line touches the graph of the function. Okay? Yeah. So that is called L. L stands for line. SEC. L secant line. And if you want to find the slope of the secant line, okay, you of course look at the difference between the y values. So you do this f of x plus h, or just this f of x is like y1, and f of x plus h is like your y2. Okay, so you do y1 minus y2 minus y1. Divided by x2 minus x1, slope of a line. Well, the top part is called delta y, and the bottom, the difference between x's, is delta x. Very important notations in mathematics, these deltas. Okay? Yeah. And if you want to obtain the line that's tangent,
Wait, is that my internet, or is he just, is he actually just gone? No, I think he's frozen.
Oh, okay.
Yeah.
Or wait a couple minutes. Gone, right? Yeah, he's gone. Okay.
I think he got kicked out. His internet was bad.
Did you kick him out?
No, I don't know why I became the host.
Okay. Yeah. Okay. I see. But anyways, how's for you guys so far? Kind of what you expected, kind of bits, not what you expected, or nice back, right? Hey, Professor, you're muted actually right now.
Spectrum booted me out. Okay, sorry about that. I got booted for some reason. Yes. So again, this is the slope of the secant line, and our goal is to shrink this h down to 0. So we're gonna bring h.
You have
And
to share your screen, Professor.
oh, my screen is not showing either. Thank you. There we go. Yes. Yeah, so I want to close the gap between x and x plus h. We want to bring that point over here, close to h, so that the secant line eventually turns into the tangent line. Okay, now to get the tangent line, you do not make h 0. Okay, we don't. If you make h 0, then what happens is that y1 and y2 become the same. x1 and x2 become the same, right? And you get 0 over 0, which is indeterminate, all right? So you don't want to make h exactly 0, because the points x1 and x and x plus h become the same thing for the y's, and you get 0 over 0, which doesn't make sense. Okay, so to get the equation of the tangent line, which is something like that, a little bit steeper. Yeah, so that's the tangent line. We're going to let h go to 0. Okay, so you take the limit as h goes to 0 of y2 here is f of x plus h, minus y1, which is just f of x, divided by x plus h, that's x2, minus x1, okay, or x. Okay, so you find the difference between these two, divided by the difference between these two. And their x's cancel out, and you get the famous difference quotient rule. Over h. And this is what we call f prime of x, or the derivative of f at x. You guys are going to be studying the three-dimensional version of this thing. You want to know what it looks like? Have you guys seen partial derivatives? Anybody? You want to know what partial derivatives look like? Yeah. So you have in calculus 3, let's just look a little bit far ahead. In Calculus 3, functions are multidimensional, okay? So you have in Calc 3, this is nothing that you're not, this is something you're gonna understand, trust me. In Calc 3, the function, instead of calling it f, or instead of calling it y, we call it z. Z is equal to us to the sum function of x and y, okay? Now, what's one of the applications of this? Imagine you have a picture, okay? You have a picture and you upload a picture onto your computer and you try to process that picture, okay? Yeah. So a picture consists of pixels, right? So on your computer screen, you see a bunch of pixels. If you've taken my Math 11, I probably most likely talked about this before, but I just think it's cool. I took 3 classes on this subject called image processing. So yeah, a picture has every pixel. Now here you have the R2. This is R2, right? It's basically, think of this R2, think of this plane right here as your, I don't know, TV screen, okay? It's your monitor, right? And you can assign a point to every pixel, right? There are, I mean, millions of pixels, right? But let's just look at some of those pixels, okay? So you have a pixel right at 1, 1. Of course, there's a pixel at 0.1, 0.2, 0.1, negative 0.5. There are so many of it, but to keep it simple, let's say these are the pixels, okay, on your computer screen or TV screen, whatever. Okay, so every pixel has an address, right? Every pixel has an address. Now, according to the address, okay, according to also each pixel has a intensity on how bright that pixel is. Imagine the picture is just black and white for now, okay? So every pixel has a number associated to it as what you might call it, like intensity, right? So if it goes from, I think, 1 to 256, something like that. So 1 means really white, and 256 is black, right? Is that correct? Is anybody familiar with that? This has been such a long time for me. Yeah, so you can assign a number to the intensity of brightness of every pixel, right? So for instance, if this pixel here is like, let's say 100, it is gray. It is it's a certain shade of gray, right? So every pixel, my screen is frozen. Every pixel has a number, so associated to it. So here, again, let's look at a certain pixel. Like, let's say this pixel right here. To it, there's a x, y. So x, y tells you the location of the pixel. And then z is the, again, the grayscale. So intensity or color intensity. And it goes from It goes from, I think, 1 to 256, if I'm not mistaken. Right? So, for instance, like let's say if z of 1, 2 is equal to, let's say, 1 or 256, it means that the pixel, so we're talking about this pixel right here, 1, 2. That pixel has a scale of, or gray intensity of 256. Okay, so this is what we call a multivariable function. The input is the location of the pixel, and the output is how bright that pixel is. Okay? Yeah. Now, what are some things you can do? Of course, you can write filters. We can write filters to like modify the image. One thing that is done a lot with image processing is edge detection. Do you guys know what that is? Edge detection. No? So you have a picture and you import that picture onto like Photoshop, and the Photoshop detects the edges, right? So if I import my face, okay, into like my MATLAB or Photoshop or something, it will detect edges, like, you know, the edges around the face, the nose, you know, the edges, the edges around the lips. Let me actually show you guys what exactly I am talking about here. Give me 1 second. This is actually pretty cool. Somebody send me something through chat. Okay, so let's share the screen. I hope you guys can see that screen. All right, so this is Wolfram Alpha, as most of you are familiar with. This is pretty cool stuff. All right, so I'm going to ask Wolfram Alpha to graph Trump for me, okay? Look at it. Here is a graph of Trump. Ain't that cool? Let me see if I can zoom in. Give me a second. What is this? Give me a second. Here we go. Let me zoom in a little bit if I can. Yeah, that is the graph of Trump. Okay? Yup. Not only that's a graph of Trump. Oh, this is not a drawing, you guys. This is not a drawing. This is actually the graph of a mathematical function. Do you guys want to see the function? Do you want to see the equation for his face? Look. I don't know if that equation is so big it sometimes doesn't show. Yeah, so it says the standard computation time exceeded. So let me graph somebody else, maybe. Tupac Shakur, if you guys know who that is. So here's a graph of Tupac. I'm waiting for the function to actually show up. Here is the function. Look at it. Look at the function for the face of Tupac Shakur. Look at it. Y'all see that? It's just, it never ends. It never ends. Whew. Yeah. So, do you guys think that somebody had absolutely no life to sit down and type this function in? Huh? Oh, let me figure out what the graph of Tupac's face looks like. Let me figure out the function that to graph Tupac's face. No, you can't do that. So what happened here? How is this done? So somebody took the picture of Tupac and they scanned it into a computer software, not MATLAB, not I'm sorry, not Photoshop, but there is a software called it's called MATLAB. Okay, there are other softwares that do this, like Wolfram, like Mathematica. And what it does is that the software detects edges of the face. You know, I look at him. You can see, of course, the edge on his head, the edge for his bandana, the eyebrow, the nose. Those are edges. Okay, those are sharp edges. So what does happen at those edges? How do we find those edges? I'll tell you how those edges are found. So computer identifies the edges the way this like whole drawing is done. The computer finds the edges first, that's step one, and then of course graphs the edge, and then it uses what's called a curve fitting method or extrapolation. Like, you know how you do like linear regression, you can fit a curve through data. So the computer does a curve fitting, and the computer comes up with this monster of equation on its own. Okay, but the way that these edges are found is got to do with derivative. Okay, what happens is that if you have an image, if you have a two-dimensional image like what I've shown you, let me share my screen here. Yeah, so if you have a two-dimensional image in space, right, and these are like pixels, and again there are so many pixels right there. There's so many here. I'm being very, I put just a few. So what the computer does is that it finds the derivative. It finds where the function z equal to f of xy fails to be differentiable. Okay, because when a two-dimensional function like z equal to f of xy is not differentiable, then there is an edge. Okay, at the edge, we're talking two dimensions here. At the edge, the function becomes not differentiable. Okay, now let me ask you guys a question. So let's go back to just typical functions, y equal to f of x. What does it mean for a function to not to be differentiable? If you have a curve y equal to f of x, geometrically, what makes y equal to f of x non-differentiable? Can anybody answer that question? Except for my mentors, peer mentors. Anybody? Geometrically, if a function is not differentiable, yes, Nicole?
It's not continuous.
Well, a function could be, there could be a function that's not differentiable, but still continuous. You're right. But
Oh, and that's when there's a like a sharp curve.
yes, good, sharp, cusp, honors, excellent. Yes, yes. So in three-dimensional version, the edge of, when you have a picture, to find the edge, the computer looks for points where the function for the face is not differentiable. Okay, at those edges like are sharp points, the function does not, fails to be differentiable. So that's an application of that. All right. Yeah, so we all kind of know what differentiability is. And let me make sure you guys can see my screen. Yes. All right, so I have this handout on there. I did not write this handout. Someone else was kind enough to do it for me from well, not for me. They've done it for the previous semesters. Yeah, so a function that's not differentiable. Look at the definition of the derivative. By the way, differentiability also means smoothness. Smooth. You'll hear that terminology in Math 11 a lot. Smooth means differentiable, kind of. Yeah. So a function that's not differentiable. Let's go over some of those. Non-differentiability detection. Trust me, you guys, if your major is I don't know, computer science, you want to get into entertainment like animation, stuff like that, you're gonna have to you really have to understand the notion of differentiability. Okay, so discontinuity is not the same thing as, or continuity is not the same thing as non-differentiable. So let's see when a function is not differentiable. So let's say that we have a continuous function. Okay. So let me know if the screen is frozen. So let f be continuous. So continuous means no holes, no vertical asymptotes, and no removable discontinuity. You can't take the point and put it somewhere else. Also, no jumps. Okay, no jump, no vertical asymptote, no holes. That's what makes a function continuous. Okay, yeah. So let f be continuous at a. All right, then we say that f is not differentiable at x equal to a if the function has a corner. So if either of the followings are true. Number one, f has a corner at x equal to a. Okay, so corner. Let's look at a corner. They in the handout, I see that they're telling you what a corner means. They tell you mathematically. I don't want to do that. let's graph a function that actually has a corner, okay? And see what's so bad about it. Okay, so what's a corner? A corner would look something like this. Okay, so let me actually use two different colors so you can distinguish between the two. Okay, so here is x equal to a. Right there. That is a corner. Do not confuse a corner with a cusp. Okay, I'll get to the notion. Cusp has to do with an infinite derivative. A cusp is when the tangent line becomes infinite in slope. But look at what's happening here. All right, if you look at the derivative from the left of a, right? So the derivative from the left of a is that, right? Just right before a, just exactly right before a, that's the derivative. But what happens is that on the right of a, the derivative becomes entirely different. It becomes something totally different. There is no smooth, listen to me, there is no smooth transition from that derivative to this derivative. Okay? Yeah. And this has got to do with the limit. It has to do with the limit. Right? So here what's happening is that I can actually use the non-H definition. I think you guys are more comfortable with that. So what's happening here is that the limit. This is, by the way, the definition of derivative at a point. Okay? So slope of the tangent line at that point, again, this is a f of a. Okay, so let's look at the slope of the tangent line. It's f of x minus f of a divided by x minus a. And here x is going to a. Now, if you're looking at the left, okay, so here's like, let's say that secant line. Here's that secant line, right? That's a secant line. This is f of x, okay? As the secant line, as this point is getting closer to a, so it's getting closer to a from where? Is it from the right or the left? You guys, the blue graph. Is it right or left? Anybody? Don't be shy to speak out. Anybody, like right or left? Okay, well, let's talk. Let's ask Ivan. Ivan, are you here? I see your tile, Ivan.
I'm here.
What up, buddy? What's up? Is this so? I'm talking about finding the derivative, right? Using the blue graph. I'm trying to find the derivative at this a. Okay.
But it's not differentiable at that point, is it?
It's not differentiable. I just want to know if I were to find a derivative right here, right? Using the blue.
Right.
right? So this is the secant line. I
But-
want to make the secant line into this tangent line. What does x goes to? So here x goes to a from where? Is it a right-handed derivative or a left-handed derivative?
Left-handed, right?
Yes, yes. On the blue graph, this is like, let's say x f of x. Okay, this is a secant line. And of course, this is a f of a. Yeah, if you want to use the blue curve, right? X is going to a. You're from the left of a.
Yep.
So that's a yes. Thank you so much, Ivan.
What
That
was-
is a left-handed derivative. Okay. Now, if you are using the red curve, this red curve right here, right? So take f of x to be here. So say this is x, this is f of x, right? So here's the, here's the slope of the secant line. If I want to make this point closer to this point, x has to go a from where? Let's ask, I called on Ivan. Dane? Dane, are you here, buddy? No, Dane? Dane Cruz.
Oh, hi. I thought that took a water. What was the question?
Yeah, Dane. So if I want to find the derivative, if I take a point on the red curve, and my intention here is to find the derivative at a, right? Using the red curve. So here's the secant line, right? And this is x. X goes to a from which side? Is it from the right side or the left side?
Would it be the right?
Yes. So that would, thank you so much, Dane. That is a right-hand derivative. Okay. And obviously, these two limits are not the same. They're not the same. It's not. So if you pay attention to the blue curve right there, the left-hand derivative looks like that. Okay? And the right-hand derivative should look something like that. Something like that. They're not the same. You can't, remember, we can't have two distinct answers for a question. It logically makes no sense, right? The definition of a function for every question, there is only one answer. Okay, but these two values are going to be different. Okay, very different, not the same. So the derivative at a fails to exist because there is a corner. Okay, we say here f of x is not differentiable because there's a corner. And when I say when a function is not differentiable, I mean it's not differentiable at a. Okay. So you guys see what a corner is. A corner, you get different derivatives, and those derivatives are finite. They're finite. Okay. So look at this graphically. From the left derivative seems to be like, I don't know, maybe like 1/2. The slope of that line is like 1/2. But the right-hand derivative It looks something like this. That seems to be like -1/2 or -1. I don't know. So at a corner, you get two different derivatives that are different constants, different constants. Okay. Now let's look at the idea for a cusp. What in the world is a cusp? All right. Yeah. So let's say to assume f of x has a cusp. Can anybody tell me what a cusp is? And please don't do this to tell me that's a cusp. Mathematically, what is a cusp? Can anybody? I'll give you guys like 120 extra credit. How's that? 120 points.
Well, I know that
I'm
the
yeah,
shape
go for
either
it.
looks like this or like this, but these two sides are going infinitely either up or down, right?
Excellent. Just elaborate just a little bit. I really like that. I really like that. So what's a, yeah, okay. Can you explain to everybody the difference between a cusp and a corner?
Well, the cusp goes on infinitely, like in that shape. The corner is just there.
The corner, the derivatives are, so the derivatives at a corner are finite. Like in the picture, the derivative, the left derivative is like something like let's say 1, and the right derivative is like -1, right? Yeah, very good. But cusp, yes, the derivative goes to infinity. Very good, actually. Yeah, and that's what's happening with a cusp. So here is an example. Maybe we do like, let's say f of x equal to, I'll do an example. Or maybe give me a second. Maybe I can pull an example quickly for you guys. Maybe something like x to the power of 2/3. I think that is going to have a cusp. Is it? X squared to the third. The derivative of that. Yeah. Yeah. So cusp. Example. Good example for it. Give me a second. Okay, never mind. Somebody's chatting. Send me a chat message. Okay. So cusp. Say we have f of x equal x to the power of 1/3. All right. Or x to the power of 2/3. Yes. Yeah, so for x to the power of 2/3, if you were to graph this, and I'm sure that by now you guys have passed what, math 7, but by now what the derivative here should look, or what the graph should look like, right? Okay, but x to the 2/3, if I do my best to graph this, it looks, oopsie, it looks something like this. Oh, let's do that again. It's like a double square root, kind of like that. Okay, that's what it looks like. And let's pay attention to 0. Okay, pay attention to x equal to 0. That's our A. All right. So what's happening here is that when you find the slope of the tangent line, like let's say from the right of 0, right? That tangent line becomes more and more vertical. That's what's happening. It's becoming more vertical. Not only it does become more vertical, but on the left of 0, it tends to do the same thing. It becomes more and more vertical, okay? But the way, and we know that if a line is vertical, then its slope is undefined. So for sure we know that this function is not differentiable. But why is it that, what proves that this is a cusp? Okay, well, let's look at the derivative here quickly. Here, the derivative function f prime of x is 2/3 x to the power of negative 1/3. Okay, or you can write that as 2/3 x to the power of 1/3, or cube root of x. Okay, so just like before, where we had to find limits, let's find the limit of the derivative. I want to know what's happening at x equal to 0. Things are fishy at x equal to 0. Okay, so if you take the limit as, this is, by the way, got nothing to do with the definition. Sorry, my dog, I stepped on my dog accidentally. Did you guys hear that? Did you hear that? Oh
Yes.
my God. He's sitting, you gotta see where this dog is sitting. Let me show you. Hey, come here. Come here. Come here. Come on. Jesus Christ. Come on, buddy. Oh man. I have 3 dogs, by the way. Two of them are not here right now, but God, man. Okay. Sorry, man. Sorry, buddy. All right. By the way, my dog is the only thing I say sorry to. I've never said sorry before in my life. Yeah. Anyway, I'm joking. I say sorry to my wife like 26 hours a day. Anyway, so going back to this thing, if you look at the limit of the derivative as x goes to 0 from the left, okay, of the derivative, of 2/3 x to the power of 1/3. Okay, so here when x becomes 0, this denominator becomes really small, really small, okay? But it's still negative because x is going to 0 from the left. So this number is something very small, but negative. Like negative 0.0001, negative 0.001. And when you divide 2 by something that is super small but negative, you end up with negative infinity. And that's exactly what's happening here. If you look at the left of 0, 0 left, okay, those tangent lines become more steep, but they become more vertical, but their slope I said slope. Their slope is still negative. So it goes to negative infinity. If you look at the right-handed derivative here, so we do the limit as x goes to 0 from the right of the derivative, not the function. Right? Well, again, here the denominator goes to 0, but it's positive. 2 divided by something really small but positive is infinity. And again, we can see that from the right of 0. Those tangent lines become more and more vertical, but they all have positive slope. So when the derivative, listen to me, when the derivative goes to different infinities, okay, when they go to different infinities, then the function has a cusp. Okay? Yes. So if the limit of f prime as x goes to a is equal to infinity, and so I should say here plus or minus infinity, and so this is from one side, and the limit as x goes to 0 from the, as x goes to a from the other side, from the positive side of the derivative, is either negative or positive infinity, then f has a cusp at a. Okay? So the way this reads as, if f prime, first one, if f prime goes to positive infinity and f prime goes to negative infinity, it has a cusp. Or if f prime from the left of a goes to negative infinity and from the right side goes to positive infinity, different infinities, then there's a cusp. Okay? Different infinities for f prime. Let me see what else I have here for you guys. Blah, blah, blah. Who can tell me what happens if the derivative goes to the same infinity at a? What is that? What is going to happen? What if the derivative, I'll write it out for you. Think about it. If the limit as x goes to a of f prime of x is just equal to infinity. So when I say x equal to a is infinity, it means from both sides it's infinity. Okay? Or if the limit as x goes to a of f prime of x is negative infinity, then what do you say? F has what? Has a, anybody? Think about it. Just don't give me the answer. 20 seconds. Think. Going to infinity.
Is it an asymptote?
Let's assume continuity.
Oh, okay.
Let's say f is continuous. Let's say f is continuous. Good job, though. Good job. But yeah, but let's assume continuity. You're very close. There's the word tangent. There's the word tangency is in there anyway.
Is there
no.
a full Is there a hole in the graph?
Whole? No. Whole is non-continuous function. It's continuous.
Oh, is it a vertical tangent line?
Good vertical tangency. Good job. Good job. You know why? Do you guys know why Nicole is nailing these questions? I don't know about the rest of you. I don't know about the rest of you. I mean, I see Max. Max is writing stuff out. Good job. I see Elena. I see myself and I want to throw up. I see Nicole. I see Nicole. And Nicole is writing stuff down. I ask a question. She goes right ahead, right to her paper, writing stuff down, and she gets it right. All right? Yo, good job, Nicole. Yes, vertical tangency. Vertical tangency. Well, why is that? Okay, so imagine the derivative. Here is the derivative. The derivative at x equal to a goes to infinity. So at x equal to a going to infinity means that from the left of a, so say here is a, from the left of a, those tangent lines become vertical and their slope remains infinity. So we have something like this. Something like that. Let me make it better.
So I think
Actually,
your screen's actually frozen.
yeah, I know it happens all the time. Okay, like that. So left of A, look, from the left of A, I drew this some in a way that those tangent lines, the tangent line is gone to infinity, right? You have a vertical tangency. From the right of A, those tangent lines also are infinite, okay? So we still have the strength. All right, vertical tangency. So right of A, the lines become more and more vertical with a positive slope. From the left of A, they become more and more vertical with the positive slope. Very good, Nicole. Good job, girl. Okay. All right, so let's go ahead and do some stuff on the handout, please. And please do not confuse differentiability and continuity. If a function is differentiable, then for sure it is continuous. If a function is continuous, it's just continuous. It doesn't mean it'll be differentiable. Just keep that in mind also. All right, so problem 1, if you look at the handout for today, let's see which one of these I want to do and which one I want to leave to you for you to do. Problem 1 says, how can a function fail to be differentiable? Each of the following functions is not differentiable at 0. Determine whether the function is not differentiable because it's a point of discontinuity, a cusp, vertical tangency, or corner at 0. Okay? All you gotta do, you guys, is take the derivative. Okay? Take the derivative and see what happens near 0. By saying what happens near 0, do not plug 0 in. Finding the limit. We want to know what happens near. Near. Let me spell near. N-E-A-R. Near 0. Not at 0. Okay? N-E-A-R, near 0. Okay, so the instruction here is for 1. You are going to find the limit as x goes to 0 of f prime of x. And you're gonna do it from both sides. Okay, so that's do it from the left, and limit as x goes to 0 from the right, because you could have a cusp or a vertical tangency. So for instance, I actually did one of these problems. Like C would be a great problem, honestly. If you've taken Math 7, there's no way in heck you have not seen C. I mean, it's just C is given and spoken by every Calculus 1 teacher. Okay, so let me get you started on C, 1C. If I was writing this handout, I would make that function a lot more complicated. Like I would have it as absolute value of x squared minus 1 over x minus 1. Does anybody not have the handout on Canvas? Let me see if I can send it, okay? Give me a moment, please. All right, some people don't have access to Canvas, so give me a moment. Here you go. There you go. There's a handout in the chat box in case you don't have it yet. All right, cool. Okay, so as I was saying, yes, C. I wanted to get you started on C, which is about the absolute value of x over x. I think I for some reason lost my own handout. Here it is. Yeah. Okay. So you want to investigate the derivative from left or right. Well, you have two options. You can find the derivative function and then take the limit of that, or you can use the definition of derivative. It's up to you, really. It's up to you. I don't know. I don't care. So here, h of x happens to be a piecewise function. It's absolute x over x. This is what I call a signal, because this function tends to jump. It jumps, okay? And you can actually find that jump, or you can use the definition. Yeah, let's just break this function down. Let's break it down. Okay, so what do we know about absolute value of x? Okay, absolute value of x, again, is defined as either x, if x is positive, now positive or 0, so I make that greater or equal to, and it's negative x if x is less than 0. And I told you guys why yesterday. And because a lot of people know this definition, they don't understand a bit of it. Again, this thing, because if, like, let's say you're finding absolute value of -1. Absolute value of -1 by this definition is the negative of here. My x is -1, which gives you positive 1. Huh? Positive 1. So that negative in the front makes it positive. And you want that's what you want. That's what you want. You want the output to be positive. So take this and divide it by x. That gives you the function h of x. Okay, so I'm dividing by x. All right, so our function is either 1 if x is positive. By the way, I need to, if you pay attention here, I include a 0. I no longer need to do that because I'm dividing by x. So here x is not in the domain. So I will gladly erase that. Okay. And the second piece is negative x over x, which is -1. That's true if x is less than 0. So that's your function. Okay. But what do you guys think is happening here, you guys? What do you think is happening? What's happening to the derivative? They're asking you they're telling you each of the functions is not differentiable at 0. Find whether the function is not differentiable because of a point of this. Is it because it's discontinuous? Is it because there is a corner? Is it because there is a cusp? What the heck is it? Why is this function? Why is f of x or h of x not differentiable? Any ideas? Go. Ivan, what's up?
I think it's a corner, right? Because the absolute value equations are usually like this, right?
Yeah, thank you. I guess yeah, for sure. I mean, okay, so now let's talk about it mathematically. Yes, certainly absolute value function has a corner, right? But what is it about the math that is telling you that we have non-differentiability? Well, you know, if you are talking about if we are talking about absolute value of x on its own, yes, you are absolutely correct. Yes, absolute value of x is not differentiable at 0, but this function is absolute x over x. So what do you think? You know, the graph of the function, you guys. Let me graph the function for you for a second, okay?
Isn't it that the function doesn't exist at x equals 0?
The function definitely does not exist at x equal to 0. That's totally right. Entirely right. Yeah. But yeah, graph of the function when x is negative, when x is positive, the graph is 1. And there's a hole here. Graph is 1.
Your screen is frozen, Professor.
Goddamn, I hate that. I know. Do you know how often I hear that every day? 30 times on average. Yes, go.
It's discontinuous, correct?
Yes, it is. This function jumps. It is a jumping function. Good question. This is the function. It's a signal. There is a sudden shift in the signal at 0. Okay, so when x is less than 0, when x is less than 0, right here, x is negative, y is negative 1, and for more than 0, it's 1. This function jumps, it is not continuous. And what do we know about a function that's discontinuous? Is it differentiable?
It's not differentiable.
Who said? It is different. I'm kidding. It's not differentiable. It's not differentiable. Right. Yeah. If a function is not continuous at a point, it's definitely not differentiable. That is the end of it. Okay? Although the derivative is 0 from left and right, this thing is still undefined at 0. It is not differentiable. Okay? So that's the reason. Yeah, so since f is discontinuous, at x equal to 0, then it is not differentiable. So continuity is a very important, very, very, very important part. That's what you have to check for first. Let's do 2. 2 says determine if the function is differentiable at 0. If so, find the derivative at 0. Okay. So yeah, I don't know which one do you guys want to take. So let's just go to the next page. Oops. Okay, I'm hoping I'm still recording. Am I? Yes, perfect. All right, so first one says f of x is equal to x squared cosine 1 over x and 0 if x is equal to 0. Okay, so remember, you guys, in order for a function to be differentiable, it has to be continuous. Okay? If a function is not continuous, it's definitely not going to be differentiable. If there's a hole, not differentiable because it's not continuous. Vertical asymptote, not differentiable because it's not continuous. Jump, not differentiable because it's not continuous. So all that stuff plays a vital role. Okay? So look at this function. To you guys, does this function seem to be differentiable at all, or continuous? Let's go with that. So first, note that, let me write that over here. Note a function or a differentiable function is continuous. Okay, so you might have to check continuity as well. Now, can anybody say if this is continuous? And we are looking at 0, at x equal to 0. Okay, so again, make sure that if the function is piecewise like this, which I absolutely hate, make sure it's continuous first, okay? All right, so question is at x equal to 0. So is f continuous? Who can answer that question? Who can tell me how to check for continuity, you all? Come on, come on. Let's take Cho, are you here? Deok Cho, help. Deok,
Yeah, I'm here.
what's up, buddy? Well, how do you think I should check for continuity? Do you remember from Calc 1? Continuous. Continuity at a point.
It should be the match the left side and right side, and then it should be
Limit,
on the plane.
right?
Yeah, yeah.
Okay, so yes, so first of all, right, we check if f of 0 exists. What's f of 0 here? I'm checking continuity at x equal to 0. So what's f of 0 here?
0.
Yes, f of 0 is 0. Obviously tells you when x is 0, f 0. Now, so we know that the function is defined at 0. Next, you need to take the derivative.
You're frozen again, Professor.
Oh gosh. Every time, if I got if I got 5 cents for every time someone said that, I would be in Punta Cana right now enjoying my time. Man. So next you check the limit as x goes to 0 of x sine 1 over x. Any ideas how to take this limit? We actually talked about it yesterday. Oh, somebody rose their. If you want, you can just speak, Ivan. You don't need to raise your hand.
Professor, how is
Ivan?
f of 0, 0 if in the first equation there with the cosine, I mean, it can be 0, right? Because 1 over x.
Okay, so cosine of 1 over x. Yes, you're right. So what happens is that, oh, is that a cosine? Sorry, I wrote sine for some reason. Give me a second, let me fix that. Yes, so you might say cosine of 1 over x, this 1 over x goes to infinity. When x goes to 0, this becomes undefined, correct? Right?
Yep.
Okay, so this is the limit. Limit as x goes to 0, this cosine of 1 over x is not going to become infinity or anything like that. As x goes to 0, that cosine of 1 over x is just going to bounce back and forth. Right? It's just going to keep bouncing, but it bounces from -1 to 1. Let me see if I can actually share my screen showing you guys what I am exactly talking about. Cosine 1 over x. It's just gonna, yeah, look, here, I'll show it to you. Give me a second, you share. There it is. Do you guys see that? Yeah? This is cosine of 1 over x. So cosine, no matter what is inside of it, it doesn't go beyond 1 and -1. It's
Right,
just as it's just bouncing back and forth, and it bounces rapidly when you're getting close to zero, right?
Okay.
So, yeah. Now, when you multiply that by x or by x squared, so let's multiply by x squared, then it's going to get sandwiched. So let's see what that does. Yeah, you see what happened to it? It is shrinking. You know that part that waved so much? So that part kind of shrunk because when you put an x in front of it, and anything that's from -1 to 1 is going to shrink to 0 because x is going to 0. Okay? Yeah. So this limit, if you want to show it using squeeze theorem, we know that cosine of 1 over x, no matter what, you have cosine of x, you have cosine 1 over x, you have cosine of sine x.
You have to switch screens, Professor. Sorry.
Yeah. Thank you. Cosine of 1 over x is always bounded. It's from -1 to 1. No matter what. How undefined, how messed up. It's, if I have cosine of e to the power of root x times, give me some weird ass function, I don't know, times like let's say sine of the 1 over square root of cosine x. No matter how ugly inside the cosine is, that thing is still between -1 and 1.
Professor,
Okay.
I'm sorry, the screen is stuck on the website that you're using, so I haven't been able to follow.
Oh, yeah. I apologize. Yes. So let me change my screen here. If I were Zoom, I would advance this platform a bit more. Okay, so cosine 1 over x. Are you guys seeing that?
I'm still stuck on the same page.
Okay, there we go.
Now it's better. Yep.
Yeah, cosine 1 over x is between -1 and 1. Multiply that by x squared. So you get x squared cosine 1 over x between x squared and negative of x squared. Okay, and when x goes to 0, so as x approaches 0, then this left bound goes to 0, the right bound goes to 0. Negative x squared and x squared both go to 0. So this limit finally is 0.
Okay, so I did this when I first saw the problem, and this is exactly what I did. But so if I do have a problem like this, and if it makes sense that from the left, negative x squared and x squared in this example, they both go to 0 when they're 0, then by squeeze theorem, we can just assume that the middle function as well is going to be 0.
That's exactly what squeeze theorem is. Yes, for sure.
So this is like a foolproof method of just making sure that.
Yes.
Right.
Method of finding the limit. Yes. Yes, you can use it all the time. All right. Yeah, so anything squeezed between 0 and 0 has got to be 0. Now, the question here is, to answer the question, is the function differentiable? So we so far determined that the function is actually continuous. It's continuous because f of 0 exists, the limit is 0 and it exists, and these two are the same, right? Yeah, so here f of 0 is the same as the limit as x goes to 0 of f of x. That's that is the third part of the requirement. Okay, so again, our function is continuous. Now you need to check differentiability. Okay? To check for differentiability, you need to differentiate the function. Okay? You need to see if the derivative does actually exist. Okay? So in order for a function to be differentiable, it has to be continuous. That's what you have to check for sure first, okay? All right, so let's take the derivative here. F prime of x is, you have to use the chain product rule and chain rule. So I get the derivative of x is 1 times sine of 1 over x. Okay, plus x times the cosine of 1 over x is the derivative of sine, times the derivative of 1 over x by chain rule, which is negative 1 over x squared. Okay, that's if x is not 0, 0 if x is 0. Simplify the mess. You get sine of 1 over x minus cosine of 1 over x divided by x. Okay, here x is not 0 and 0 everywhere else. Okay, so this is the derivative function. I don't know what happened. Okay, so this is the derivative function. And then what you do again, yeah, this is the derivative, the simplified version of the derivative function. Okay, so what you do here again is try to find the limit at, so this is when x is not 0, the first one. Yeah. So try to find the limit of this guy. We are checking for differentiability, just like the way we did for the previous problem, right here or right here. Yeah, so that's what you guys have to do. Now, what happens is that the limit of sine of 1 over x, as x goes to 0, this limit, I don't think it exists. Let me look at the graph over here quickly. Give me 1 second, and then we also have to take a break. I gotta make sure you guys take your break. Sine of 1 over x. And I am doing problem 2. X squared cosine 1 over x. So I'm not sure what happened with my derivative. This derivative should have been a 2x.
Professor, I think it's supposed to be 2x cosine 1 over x.
Yeah. One of my derivatives is not. So yes, I see what's going on. That should have been a 2x, right?
Yeah, I was gonna say I got a different.
2x,
Yeah.
and then this should be x squared. Okay, so that fixes everything. So yeah, I'll just write this thing down. Oh my God, this is getting pretty annoying. Okay, very good though. So the simplified derivative is 2x cosine of 1 over x. I don't know how I got the previous derivative. I just have no idea. And then we have plus sine of 1 over x. Sorry about that. I have no idea how I got my derivative here. Okay.
You're frozen again, Professor.
Of course I am.
I got minus sine 1 over x, but I could be wrong.
Minus the derivative of cosine is sine, right?
It's actually negative sign.
Okay, let
And
me,
then-
give me a moment, please. Let me fix that. Let me fix
Oh, no,
that. Just
Professor,
give me
your- I
1 second.
believe your derivative was right.
Yeah, it's correct because the negative cancels out with the
With the
negative once you
negative.
take the derivative
Yeah,
of 1 over x.
yes.
Oh, it's because the derivative of cosine is a negative sign, right?
Yes, it is.
Okay, then it's positive.
So that should be just sine of 1 over x, right? Yeah. Okay, cool. Okay, so now you guys are going to investigate the limit from the right and left. Okay, and I doubt the limit is going to exist. The limit here is not going to exist for sure as x goes to 0. Okay, because you have that sign of, you have the sign of, what is it? Sine of 1 over x, and the limit of that, this limit is actually a DNE. Okay, so it's not going to exist. Yeah. Not a cool problem though. I don't know. Not a fan of it very much. So let me look at the next problem or problems before we run out of time. Let me see what is a good problem to do here. Yeah, these problems are not bad at all. So are you guys are familiar 100% with quotient rule, chain rule, and all that stuff? Is there anybody here wants me to go over chain rule, quotient rule, product rule? If
Maybe
so,
briefly-
please let me know.
Maybe briefly, if it's possible, just to get a refresher.
Yes, for
Yeah.
sure. Yeah. So we have the derivative rules. We have the most important rule of all, which is the power rule. The power rule says that if you're taking the derivative of some function,
You're
x
frozen
to-
again, Professor. Sorry.
I know, x to the power of n, the power rule, the derivative of a power term. This is n, x to the n minus 1. We are all familiar with that, right? Yeah. If you're, we have the product rule, which says that if you're finding the derivative of the product of two functions, f of x times g of x, okay, then just do the permutation of the derivatives. So you take the derivative of the first factor times the second factor plus the leave the first factor alone times the derivative of the second factor. Product rule. And then we have the quotient rule. And that's the derivative of the quotient of two functions. Which is, this time, unlike the product rule, you do, again, the derivative of the top times the bottom, but this time minus top times the derivative of the bottom, and then you're going to square the bottom g of x. And then we have, of course, the chain rule. Which says that if you have the derivative of a composite function composite, then you do the derivative of the outer part, f prime of x, f prime evaluated at g of x, and multiply by the derivative of the inner part, g of x. Those are the only rules, derivative rules. Unfortunately, there is no integration rule. There are integration methods, but these derivative rules proven to work all the time. All right? So you should be able to do that.